limit, yield stress, ultimate stress, and fracture stress. Okay, and considering strain, we talked about the elastic strain, the ultimate tensile strain, and the fracture strain. Okay, now now we ended up our class in the day before yesterday that this representation, the stress and strain representation, is engineering stress and strain, right? So we can correct in order to get the correct data, we can modify this graph based on the instantaneous change in length as well as instantaneous changes cross sections of the samples during straining, and based on that we can represent the stress versus strain data to get the true stress strain curve, right? Now, now the thing is, here we in broad sense we have separated this particular curve into two parts. Like one is elastic strain region and elastic region, and another is the plastic region. Now, now in the previous class we said that the purpose of elastic strain region, or in order to analyze the elastic region data, the engineers basically follow this particular region in order to design particular specimen. Like if you want to design a concrete structure, then the elastic region is the main important part. Why? Because elastics are concretes are highly brittle, and if you do the tensile test, then you will find that the materials will fail even in the elastic regions. That means the material will not go into the permanent deformations or the plastic region. So considering that particular things, the civil engineers or the construction engineers basically follow the elastic region, or the regions surrounded by the elastic stress and strain. Okay. Similarly, for the design of spring, they are also, or for the development of the glass material in this particular region. So this elastic region is very important. Now, besides the elastic region, we can consider the plastic region for the manufacturing purpose that I said, like for the productions of for giving the complex shape of a material. Okay, either by mechanical deformations or metalworking processes like rolling, forging, extrusion, stretching of a metal, or metal sheets, or even metal wires. Okay, so in that way we can manufacture that particular specimen. Now here is some limitations also available. Okay, like can we use the whole region, plastic region, for manufacturing purpose? So what will be your views? Hello, are you listening?
Sir, whole plastic for manufacturing.
Yeah, my question is, can we consider the whole plastic region for manufacturing, or to some extent we can consider?
Sir, so up to strain hardening we can. Ultimate stress.
Someone is waiting in the lobby, I think. He's informing in the group.
Sorry?
That he's waiting in the lobby. So someone is waiting to join actually in the lobby. He informed in the group just now.
Yeah, but I cannot see his name actually, or I cannot see that he is waiting for me or not.
Okay, sir. Okay, sir.
So whoever is coming, I just accepting him or allowing him to join. No problem. Yeah. So can you please give me that particular answer? That I think someone is telling
Yeah,
something.
yeah, sir. So actually, for certain applications, like if I talk about metal forming, then we cannot cross the ultimate stress. But if I talk
Yeah.
about machining, then we can exceed the fracture stress. So we can
Yeah, yeah, very
actually,
good, very good. Why? Can you please explain that why? Your answer is perfectly all right.
yeah. Basically, sir, if I talk about material forming, then we do it between in the yielding and the strain hardening region, mainly in the strain hardening region. And if I talk about metal cutting operations or finishing operations, we do it in the
Yeah,
neck.
but my question is why? My question is why?
Uh,
Why not we cannot go beyond that UTS? My question is clear, na? Am I audible? Hello?
yeah, yes, sir. Yes.
হ্যালো, হ্যাঁ হ্যাঁ বলো যে আমরা কেন ইউটিএস এর পরে যেতে পারি না
Then
ডিফরমেশন
crack
দেওয়ার জন্য বা
formation may occur, sir, after UTS, because
yeah,
making.
yes, the crack formations may occur. Means we don't know that what will happen. Either crack formations, either necking initiations. Like if certain cases where the tensile, the tensile loading is applied on the material, then maybe the necking will start. Okay, or maybe some notched kind of regions will come into the pictures. Then yeah, stress concentrations will come into the picture. Okay, so in that particular case, so that is why we generally follow the strain level up to the ultimate tensile strength. Okay, not beyond that, because beyond that what will happen, the softening kind of things will happen. Okay, so that is why you will see that in engineering stress strain curve, beyond the UTS, the load will drop, and the curve will go down from the UTS stress level. Okay, so there are lots of mechanism behind that, like that I have said, that softening mechanism, or here the hardening mechanism will come into the pictures. Like the defects will generally generate, like these defects are called the dislocations. So dislocations will generate, they will interact with each other, and they will not move. Actually, when they will interact with each other, no? So they will impede their motion, and when they will impede their motion, the material experience the resistance to deform. So that is why you will find that in order to overcome that resistance, you have to apply more amount of load. And when you apply more amount of load, then the material will again start to deform. So that is why you will find that from YS to UTS, the curve will gradually increasing. Okay, and beyond that, what will happen? Beyond that, the necking may start, and when the necking may start, then the diffusion kind of things will come into the picture. And the localized for that particular deformation cases. Okay, and that is why we may not take the risk, like during manufacturing process, we may not go beyond that particular load. Because at the UTS point, that is, the materials is experiencing maximum amount of load, and if you give more amount of load, then obviously the materials will start to fail, either by forming some crack, or by forming some necked region. Now the thing is, can we calculate the yield stress, UTS, whether considering the engineering stress strain concept as well as a true stress strain concept? Can we calculate that? And can we correlate with each other, engineering stress strain with the true stress strain?
Yes, sir. We can correlate each other.
Hello.
Yes. Yes, sir.
Hello.
We can correlate.
আমার কি
Yes,
কথা
sir.
কাটা কাটা আসছে?
Yes, sir.
Hello.
মাঝে মধ্যে কাটা কাটা আসছে স্যার।
So let's say we are trying.
আপনার কথাগুলো মাঝে মাঝে
Yeah, let's say we are trying to find out the ultimate tensile stress. So what will be? Okay. Now can you hear me? Hello.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
হ্যাঁ, ঠিক আছে, বলো যে আমরা যদি if we want to calculate the ultimate tensile stress, then and if we know the load, then how we can calculate that? From the basic stress equations, we know that the stress is load divided by area, right? So in engineering stress calculations, obviously, if we know the maximum load and then by dividing it with the gauge cross-sectional area, then obviously we will get the ultimate tensile stress, right? But what about the true stress? How we can correlate with that? How we can get this true stress at max at a or at a ultimate tensile stress position?
So there is
that
a
is
formula.
engineering stress into 1 plus the strain value, 1 plus
Okay, so in that particular cases, we can derive the equations, and then finally we will get that the true stress is equals to the engineering stress into engineering strain plus 1, right? So here you can derive by your home, okay, and then you please try to correlate. But this is the simple things, okay. But the thing is, when you want to calculate the fracture strain, okay, fracture strain and fracture stress, then the same formula will be applicable. But the thing is, when you are trying to calculate the true strain from UTS to fracture, then what equations you will follow, how you will calculate that particular strain.
So by measuring the gauge length at fracture and at UTS position, we know the phase of the, if we know the length of the sample at fracture and at the UTS position, then ln of final by initial length, natural logarithm.
My question is clear to you, na? Whatever I have asked, that is the strain between UTS to fracture, okay? What actually happened at UTS level from the physical, appearance point of view?
Necking starts.
Necking start. Then here the gauge length will be the correct one for measuring the true strain. Taking the gauge length will be the correct approach. That is why I'm asking actually, because from YS to UTS it is correct. Your approach is correct, but from from UTS to fracture stress, will that particular approach be okay, or we can modify? We need to modify that one.
I think we need to modify some.
Then how we can modify that one? Okay, when necking start, then what are the things that actually changes during straining?
Cross-sectional area reduces.
Cross-sectional area reductions generally happen, right? So can we think of that we can correlate the strain irrespective of gauge length? We can take the change in cross-sectional area. Can we take that one? If we take that one, then how we can correlate?
So because the volume remains the same, so
volume remain the same. So we can replace the gauge length in terms of cross-sectional area, right? Because this is only the localized deformation region. So we can consider the initial the initial gauge length. Initial cross sections of the gauge, as well as the instantaneous cross sections of the gauge, right? So in that way we can think of, or one thing you can do that you can take the cross-sectional area at the UTS point, and then you can take the instantaneous cross sections of the gauge. Okay, so in that way we can divide it the different different points, like true fracture strain, true uniform strain, true local necking strain, something like that. Okay. Now, okay, then that particular equations we will talk about a little bit later. But just tell me that considering the energy, how we can divide this curve into two energy regions. Like if we consider the elastic regions only, then we can calculate the resilience of that any particular material, okay, or the energy required to deform a material elastically, okay. So that particular region, this particular region is called the resilience property of a material, okay. Now this resilience actually is the ability of a material to absorb the energy when a metals deform elastically, and if we unload then it will come into its original position. So it is quite a reversible process. So if I want to calculate the energy, then what will be the governing equation?
the resilience.
Yes. The elastic energy.
Half sigma into epsilon. So the epsilon will be the strain up to the yield stress region, and sigma will be the yield stress value.
Okay, then by following the Hooke's law, we can also simplify that particular equations because Hooke's law says that you can correlate it with the elastic modulus, right? So any one of these stress strain, if you are able to find out, then by knowing the elastic modulus of that particular material, you will be able to calculate the resilience. Now the point is what actually elastic modulus tells us. Means, is it same or for let's say copper or for steel, or is it different for different material, and which property actually decides the elastic modulus of a material?
Elastic modulus, so basically it is the resistance of the substance to being deformed elastically, means when a stress
Hmm.
is applied.
তো মানে
And
কে অ্যাকচুয়ালি রেসপন্সিবল মেটেরিয়াল মানে obviously we need to go for atomic scale and there um, the binding force between two atoms is basically the responsible for the elastic modulus মানে একদম সিম্পল ভাষায় যদি আমরা বলি so the modulus of elasticity is a measure of stiffness of a material means for higher elastic modulus material they are much more stiffer than the metals which shows the low elastic modulus. Okay, so that is why actually the designer people are they mainly focused on the elastic modulus of a material, and based on that they actually design the component. Okay, let's say you are preparing a beam, okay, and during wind so beam may deflect to some extent. So if you know the elastic modulus of of that particular beam so then you will give the allowance of a beam to deflect up to a certain extent. Okay, that means you need to calculate the strain, elastic strain. Okay, so you need to calculate the elastic strain or maximum allowable elastic strain, okay, corresponding to the elastic stress. Okay, and that is why you need to calculate the Young modulus of a material. Okay, so in that way you can think of. Now, this elastic modulus for a material may change with temperatures and alloy compositions. Okay, because the concretes are may be made up of different constituents. Okay, so you can change the elastic modulus to some extent. Now. Now coming to the plastic region, so here similar to the Brazilians, okay, you can also calculate the toughness of a material during tensile loading, during uniaxial tensile loading. So in order to calculate that, you need to measure the area under the curve. Okay, so in that way you can calculate. So in roughly, people generally try to find out the ultimate tensile strength and the fracture strain, and then they just multiply it with each other. But that is the approx toughness values, okay, of a material. Sometimes they take the weighted average of ultimate tensile strength and the fracture strength, something like that. But if you are able to measure the true area of this particular curve, that means area under the curve, then you will be able to calculate the true toughness values of a material. Now, what is the importance of toughness? Can you please explain me that? What is the importance of measuring the toughness of a material, or if a material have the high toughness, then এটা কিভাবে আমাদেরকে benefit দিতে পারে?
So it can absorb more shock vibration, means more energy.
Yeah, it basically it absorbs the more amount of energy during deformation, that is permanent deformation.
Yes.
Okay, so roughly or indirectly you can say that different loading condition also it may absorb the energy, maximum amount of energy, or the energy which is relatively high as compared to the other samples one. Okay, so that is the significance of the toughness of a material.
yes,
Okay, so I think that particular things I already covered, like the measurement of the stress and strain, and here considering the true stress and true strain, you can follow this particular equations and you can correlate with the engineering stress and strain. But here one limitation is that this particular equation you can follow up to the UTS level, okay, and where you can use the gauge length of that particular test material, okay, initial gauge length and the final gauge length. Okay, but when it goes beyond the UTS level, then the applications of gauge length will be erroneous, will give some erroneous value. Okay, so that is because the total gauge beyond the UTS total gauge length will not take part into that particular the activity. Only the reduced cross sections will take part into that particular activity. So that is why you need to consider the cross sectional area of that particular samples. Means instantaneous cross sectional area with the original cross sectional area of that particular sample. Now here this is a representation of engineering stress and strain curve with the true stress strain curve. But here this curve may be a little bit erroneous because we cannot say that the may be erroneous because why maybe that is because you don't know that after UTS when the necking start which one will be dominated. Okay, like the decrement of load will be dominated or the decrement of the cross sectional area will be dominated. So based on that you can this particular curve nature will change. Okay, so that is why roughly you can get this sort of curve, but if you want to measure correctly, then you may find that here your curve will gradually increase, or where you can say, or we can see that till the fracture, the true stress will gradually increase. Okay, so this is the representations of ductility, means how you can calculate the ductility of a material considering the gauge length or considering the reductions of the cross-sectional area. Okay, but considering the gauge length, you can measure up to the UTS that I said several times, but considering the cross-sectional reduction in cross-sectional area is the most accurate part for measuring the ductility of a material. And this is the modulus of resilience and the toughness of a material. Now you can see that in this particular graph that how the toughness can vary from different material, like from softer to harder material, from concrete to metal. Okay, so you can then you can compare it with each other. Now, as I said that you can also calculate the true fracture stress where you need to follow a certain equations like or you need to find out the fracture the length at the fracture strain level. Okay, or you can use your previously known cross-sectional area of the samples. Okay, so roughly you can represent the true fracture stress by determining the fracture, the fracture load divided by by measuring the cross-section area at that particular load level. Okay, so you have to manually or mechanically measured, and then you are able to find out the fracture stress. Now, corresponding fracture strain you can calculate by knowing your the cross sections at the fracture load. Okay, by knowing the initial cross sectional area of the gauge. So if you want to represent that, then it would be the ln A0 by AF. Okay, so please try to calculate that one. Then the true uniform strain you can also calculate. So here, in order to calculate that, the equations would be ln A0 by AU. That means here you need to find out the cross-sectional area before the necking or when the necking will just start. Now the true local straining, that means the strain level from UTS to the fracture, and if you want to calculate the instantaneous the component strain component, then of course you can use the true local strain equations like ln AU by AF. Okay, that means the cross-sectional area at UTS level with the cross-sectional area at the fracture strain level. Now, in general, we can see that. Just hold on. Okay, so in general, we can say that this kind of curve you can see for mild steel or for low carbon steel, where you can find out the yielding at this particular regions generally happen at constant stress level. Okay, though the cross sectional area will increase, will decrease the length of that particular specimen. Will increase, but the significant improvement of the stress will not increasing. So at that particular zone, you can say it as the yield point phenomena. Okay, so here why the load is not actually increasing? What kind of deformations mechanism is actually happening? Can you do you know that particular things? Hello.
So can you please repeat, sir, one time?
My question is, certain cases you will find that your curve will follow like this, your curve will follow like this, and the fail material fails happen. Okay, but for low carbon steel, okay, or the mild steels, you will follow this sort of pattern. Okay, where up to a certain regions, the stress of that particular specimen is not increasing, but the straining is happening. Okay, quite rapidly. So at that particular region, so what actually happening? As I said, this particular zone shows that material, the strain hardening is happening. But what happened in this particular region?
So
Why strain
actually,
hardening is? Yes.
dislocation just starts to form actually.
No, that will be not the correct answer. Any other views that you can share? For your kind information, dislocation generally starts well before that particular zone. Okay. Can you please hold on for a second? थोड़ा टाइम को थोड़ा मेंटेन करके एक बार देखो ना, टाइम को थोड़ा। हाँ, बात तो सही है, बात तो सही है। नहीं तो एक काम कर सकते हो, पहले एसीएम करके देखो ना, तो उसके बाद Hello. Sorry for the interruption. Okay, so now where we are, yeah. So here actually what actually happens, the steels that I have said, that low carbon steel or my steel, no? So basically it contains the interstitial alloying elements like carbon and the nitrogen may be there. Okay, so those are actually blocking the dislocations motions in a certain way, uh, the dislocations actually defects are generates, and the carbons and nitrogens are sitting in those defect area. Okay, and it will resist to propagate that particular dislocations from one atomic layer to the another atomic layer. Okay, by increasing a load a little bit. Okay, so that is why and when that particular barrier just crossed, okay, with changing a little bit amount of stress, and then again the stress will fall down. Okay, so that is why you will just find some zigzag area at that particular zone. Means if you zoom at this particular zone, okay, means by taking the actual data, then you will find that first it will increase, then decrease, then increase, then decrease, something like that. So that is why for this type of curve, you will find that there are two yield stress values, like one is upper stress values and another is lower stress values. Like if you zoom this particular zone, then I think certain cases you will find. Okay, here you can see that the stress is relatively high, but at that particular position, the stress is low. Okay, so that is why you will find that the upper yield stress as well as the lower yield stress. But in case of this type of graph, you will not find this set of things. Okay, um, and you can roughly say that this set of curves you will find for high strength materials. Okay, or even you will find that for this type of curve for a high strain hardened materials like aluminium and copper. This set of materials will not show very high amount of strength, but strain hardening is very high. Okay, now the thing is, up to elastic limit, we can correlate this particular curve, okay, or this particular graph, or we can define this particular graph. But what about the entire graph? Can we get certain empirical equations which are able to describe this particular curve? Do you know this sort of equations? Hello?
Sir, sigma equal to k epsilon to the power n.
Yeah, sigma is equal to k epsilon to the power n. What is n?
Strain hardening coefficient.
Strain hardening coefficient or exponent. Okay, what about k?
K is a constant. I don't remember. What about
There is the strength coefficient. Okay, so you can follow roughly for describing this sort of curve. Okay, but you cannot say that that particular equations will exactly follow and it will superimpose the curve like that. Okay, so it is not that. Just roughly, this is a power law, simple power law formula or sort of relation. So you can just follow this sort of curve. Okay. And if you just do the log of that particular equations, you will be able to calculate the strain hardening exponent of a material. Okay, so or either you can take or separate the data from YS to UTS, and then if you just take the log of that particular data, and then you will be able to calculate the strain hardening exponent of a material. Now the strain hardening exponent can vary from from zero to one level. So do you know the importance of this strain hardening exponent?
Sir, the n value means if n value is higher, better formability actually in workshop means it is easily formable if higher n
Is it?
value.
Is it so? I have said that n value generally varies from 0 to 1. Okay. So if n is equal to 1, higher value means higher value means that the 1 is a maximum value. Okay. So if n is equal to 1, so how how it will be your curve, because k is constant, na? So the strain obviously is there. So if k is constant, it has the same unit as stress, right? And the strain has no unit, so it will be just multiplied with the k will be just multiplied with strain, right? So then how you can get this particular things if n is equal to 1? Will it show some sort of strain hardening or something?
Sir, in sheet metal forming, in value is important.
So curve will be linear with.
Just think, huh? Just think. Okay, for your kind information, that if n is equal to 0, that means that is for perfectly plastic material. Okay, that means if you want to start to deform your material, then in that particular cases you will not find any sort of elastic deformation. Okay, but yes, but the value of n actually decides that how fast material will deform, or how the materials is experiencing some sort of resistance to deformation. So all these things you can be able to determine by knowing the n values. Okay. Now it will be better if I give an examples like for 0.05% carbon steel, then you may find that the n values will be relatively different as compared to the carbon steel, let's say for 0.6% carbon steel. Okay, so in these two cases you will find the different n values, and by knowing the n values also you can determine the material property, you can determine the mechanical properties of a material. Okay. Now, but this sort of parameters is not the sufficient for determining or for judging a material mechanical performance. Rather, a combinations of those properties you need to know. Like you can be able to calculate the n. Of course, it will be useful. Certain cases you need to determine the strain hardening, exponent. Sorry, strain hardening. That is the d sigma by d epsilon. You can calculate, because the equations sigma is equal to k epsilon to the power n. So if you just try to find out the rate of strain hardening, then also some parameters you can determine, some things you can determine. Okay, if you just do the derivative of that particular equation. So let's say you are calculating the strain hardening, the rate of strain hardening, that is the d sigma by d epsilon. Then ultimately you will find like the n d sigma by d epsilon is equal to n into sigma by epsilon. Okay, so this sort of equations you will find. Then at different positions you can find at what rate this sort of strain hardening is happening. That means at these positions what will be the strain hardening, at this particular positions what will be the strain hardening, at UTS level, UTS point or ultimate tensile stress, what will be the strain hardenings, you will be able to understand, or you will be able to find out. And in this way you can understand that initially how it is deforming. Okay, but general sense can say that initially the first deformations will start, but gradually when the lots of dislocations have generated, so in that particular cases you may find that the resistance is gradually increasing. Okay, so So in that particular sense also you can think of, okay. But when the necking starts, that means when you exceed a critical value of that particular stress, then again abruptly the material start to deform, okay. So in this way, the designer peoples or manufacturing peoples can set their, the applied load values uh, um, for the design purpose or for manufacturing purpose. Now, as you said that the sigma is equal to k epsilon to the power n is the basic equations, but there are other lots of equations are available like Holomon equations. Okay, modified CJ analysis you can also follow. Okay, so the task is you please try to find out the equations which generally followed by the researchers or by the engineers to construct or reconstruct the stress strain curve. So you please try to study that particular part. Apart from the basic equation that you have said. Now, previously, I think I forgot something. Like I have said previously, I said that we need to give the velocity, cross-head velocity, or we need to tell the cross-head velocity to do the test, right? So let's say I have said the cross-head to set the cross-head velocity of 1 mm per minute. Okay, so can you please determine the strain rate of that particular test that I have followed? Can you make a correlation with cross-head velocity with the strain rate? Hello? Hello? Hello?
Yes, sir.
Yes.
So can you make a correlation with strain rate with cross-head velocity? Do you know the unit of velocity?
Yes, sir, but length is required. Actually,
What is dV? What is dV? Or V? L by T, right?
yes, yes.
What is strain rate?
Strain rate actually means that one by T.
Epsilon with
And that is 1 by T is a unit. Okay.
Yes.
But you can represent the strain rate, that is d epsilon by dt, right?
Yes.
So if you derive the strain rate like this d epsilon by dt, so instead of writing d epsilon, so you can put the value of epsilon directly there. Okay, so epsilon, if it is the epsilon, that is del L by L. Okay, so what would be the equation? dl by
dl by
dt.
dt by
dt into L, right? So dl by dt, it is defined as velocity, correct?
yes. Velocity.
So that means velocity by L0, right?
Yes.
So if you know the velocity of a material, the cross-head velocity, then you just directly put the cross-head velocity, and you can divide it this velocity with the gauge length. Then you will ultimately get the strain rate of the material of the test. So have you understood the process?
Yes.
Yes, sir.
So that is why the importance of gauge length here also reflect with your the test parameter like strain rate. Okay. So all this correlation you please try to understand, and all those parameters that I'm trying to find out, those parameters will be needed for the assessment, material assessment or material mechanical performance assessment. Okay. So in the next class, I think Saturday we have class, so we will try to finish to this particular part. Okay, that is tensile test, covering the lot more things like instability. Okay, instability in tension. Okay, and another things I forgot to mention, that we always talked about the specimen dimension, the specimen, the elastic and plastic property. So in order to get the accurate value, is it the only way to consider the results that we will get, or we need to consider the other things also regarding the machine's property? Can you get my point? Hello?
So can you explain once again the question?
The question is, we are talking about the materials property. That means our interest material property, right? Means we are trying to find out the tensile property from strength to strain. Okay, and during testing, we always are focusing on that where the material is starting to yield. Okay, where the ultimate tensile stress level reached. Okay, but we are not talking about the machine's mechanical property, right? Machine may also deform, either it is elastically or it is plastically, depending on the load you are applying. Okay, so in order to get the accurate value of the things, you also need to think of your machine's mechanical property, because you are using the machines that also made of the either it is steel or it is superalloy or it is sort of ceramic material. Okay, so during measuring the mechanical performance of your interest material, you also think of that what sort of machines you are using and what are the mechanical properties of those machines. Okay, so that is the basic purpose of my comment. ঠিক আছে? So whenever you will see, or you will see this kind of things, you also parallelly think about the mechanical properties of this machine, means elastic and plastic properties of the machines also. So we will also talk about these things with giving some equations, okay, constitutive equations. Then I think you will be able to understand quite clearly. ঠিক আছে, আজকে আপাতত এতদূরই থাক। আমরা নেক্সট পরে আমরা আলোচনা করব এই বিষয়টা নিয়ে, and we will share this particular slide after covering this particular chapter.
হ্যালো স্যার।
হ্যাঁ, বলো।
স্যার বলছিলাম যে স্যার কলেজ তো স্যার 3 তারিখে খুলছে স্যার, তাহলে নর্মালি স্যার ফিজিক্যাল ক্লাসগুলো কিভাবে নেওয়া হবে?
ফিজিক্যাল ক্লাস যদি বলে, ইউনিভার্সিটি যদি আমাদেরকে বলে, তাহলে আমরা অবশ্যই স্টার্ট করে দেব। এন্ড আমাকে একটু জানতে হবে যে গতবারে কিভাবে হতো না হতো। হ্যাঁ, এটা প্রবাবলি আমাদের ডিপার্টমেন্টেই হয়, তোমাদের সবাইকে আমাদের ডিপার্টমেন্টে আসতে হতে পারে, তো সেটা আমরা জানিয়ে দেবো। হ্যাঁ,
ওকে স্যার।
ওকে। তোমরা কি নোটিশ পেয়ে
3 তারিখে খুলছে? কখন না স্যার?
হ্যাঁ, আগে নোটিশটা পাও। হ্যাঁ
স্যার, এটা মানে এখন চিফ মিনিস্টার বলেছে স্যার।
তো নোটিশ পেলে আমাকেও শেয়ার করে দিও, ঠিক আছে? ইভেন যদি আমি অবভিয়াসলি তোমাদের আগেও পেয়ে যেতে পারি, তো তবুও তোমরা যদি নোটিশ পেয়ে যাও আমাকে শেয়ার করে দিও। হ্যাঁ,
ওকে স্যার।
ওকে, থ্যাংক ইউ।
থ্যাংক ইউ স্যার।
Thank you, sir.
ওয়েলকাম।